Morning, welcome to this session. This session will try solve a problem on general case of force system which is in equilibrium. The speciality of this problem is we will try handle the uniformly distributed force. This is what you see, the uniformly distributed force, okay, acting for 2 meters, right? So this will try. Yeah, so this is the question. The question is to determine the support reactions for the beam shown below. Okay. Yeah. So for whatever problem we need to solve, we need to draw a free body diagram. Okay. So let us try free body diagram. So I'll draw a member AB first, which needs to be removed, okay, from this system. So you see, support B is a roller. So you can expect one reaction. I call it as R1. Okay. Support A is a hinge. So you can expect two reactions. One is R2, other one is R3. One vertical and horizontal reaction. And you see there is a UDL, okay, acting till this from here to here. Okay. So this is UDL given, which is 2 kilonewton per meter, equally distributed for 2 meters. And exactly at 1 meter after this, the end of the UDL, or 2 meters from right, you have an inclined force of 1 kilonewton, which is at 30 degree. Okay. So now let us try convert the inclined force into two components. So this is by rectangular components, okay. So these two are its components. So this will be 1 cos 30. Vertical component will be 1 sin 30. Okay. Yeah, now what to do with this UDL? Okay. So first you need to convert that UDL into a point load. So how to reduce UDL from UDL or uniform force to point force? Okay, how do you do that? Okay, so you simply multiply, let us say the total load value is equal to W. So small w is the quantity of this distributed force multiplied by the length of that UDL. Okay, so which means this small w is 2. For what length it is acting? 2 meters. So total 4 kilonewton, because the units of this one is kilonewton per meter. Into the length units is meters. So what you get is kilonewton. Okay. Yeah. So it is like very simple logic here. For 1 meter span, the total load is distributed, which is 2 kilonewton. So for 2 meters, how much is the load which is being distributed? So such is the simple calculation. So we'll simply multiply the load distributed load value with the span or the length of UDL. What you said 2 meters is length of UDL. Okay. So this is how you convert the UDL into a point load. Now you remove this UDL and place a point load. Okay. Yeah. So I'll do it here itself. We'll go with a different color. Okay. Now exactly at the midpoint. Okay. Which is 1 meter from this end or 1 meter from the end of the load. Exactly at 1 meter, you have a point load, okay, which is 4 kilonewton. Now you can remove this UDL and apply this 4 kilonewton, okay. So now you can draw a final diagram by reducing it to a UDL reduced to point load, okay. So I call this as reaction 1, reaction 2, reaction 3. Now you see there was UDL here. Now I remove that UDL and I place a point force which is calculated, total value 4 kilonewton, which is 1 meter from this end. Okay. Now there was a 1 kilonewton inclined load, 30°. Okay. So that is being resolved into two rectangular components. Okay. So one is horizontal, the other one vertical component. So here it is 1 cos 30, 1 sin 30. So now this is the final member to be dealt with. This 2 meters total. Yeah, from here it is 2 meters. Okay. So the rest of the span is 1 meter. Total span being 5 meters given in the problem. Okay. Yeah, now you apply equilibrium equations. So let us say sum of x forces 0. Okay. So if you do this by taking rightward force positive, okay, let us assume the rightward force is positive. So R3 is plus minus the component here. This is horizontal. 1 cos 30. So only two forces in horizontal direction. So we get R3 value. So R3 is equal to 0.866 kilonewton. So this is horizontal reaction acting at the left end. Yeah, going for the other equations. Sum of vertical forces 0. Let us say upward forces are positive. So you can see there is R1 plus R2, the two reactions which are upward, R1 plus R2, both are positive, and two vertical forces, this one and this one. That's all. Okay. So it is -4 minus 1 into sin 30 is equal to 0. Okay. So which means R1 plus R2 is equal to 4.5. So this is the equation that you get. Yeah. Now the one more equilibrium equation. Sum of moments is equal to. So how you apply this equation? Choose any one direction as positive. Let us say clockwise moments are positive. Okay. And you choose moment center. So let us say I choose A. Okay. Moment center A. So for writing moments, I'll quickly draw the beam again so that it will be there for ready reference. So this is R1. I named it as R1, R2, R3, and so dividing this into 4 kilonewton point load. This is 1 meter. This is being UDL before conversion, and there is a load which was actually, so this was the force 30° being resolved into two components. So now you have a horizontal and vertical component, 1 into sine 30, 1 into cos 30. So this distance being 2 meters, okay, from right end, from B. Yeah, now write moments about this point A, okay. Yeah, so these two forces R2 and R3 do not produce any moment because they are passing through A, okay. So now coming to 4 kilonewton, force is for perpendicular distance is 1 meter, and this is trying to rotate this member clockwise, so plus. Now coming here, there are two forces here. One pass through A, so moment is 0, and this one, 1 into sine 30 is the force multiplied by the distance. This is 1 meter here. So from A, perpendicular distance to this force, 2 plus 1, 3 meters. Direction, again you see this about this point, this force is trying to rotate this member clockwise. So plus. Okay. Now the last one is R1. Okay, perpendicular distance from A, it is 5 meters. And this force is trying to rotate this member in this direction about A, okay, which is anti-clockwise minus, which is equal to 0. Yeah, if you solve for R1 from here, we'll have R1 value, which is 1.1 kilonewton. Okay, yeah. So earlier we had an equation with the R1 and R2. So now substitute R1 here, we'll get R2 value, which is 3.4 kilonewton. Okay. Yeah, so now these are the three unknowns which we are able to solve. So R1 is 1.1 kilonewton, R2 is 3.4 kilonewton, 3.4 kilonewton, and R3 is 0.866 kilonewton. So this is just by converting this UDL, that there was UDL given to you here. So by converting this UDL to point load, this is possible. Okay. Yeah, so this is the complete solution when you have UDL on the member, right? Thank you, and we'll be back with the next example.